Secure Shell, or SSH, is a cryptographic network protocol to allow remote login and other network services to operate securely over an unsecured network. SSH provides a secure channel over an unsecured network in a client-server architecture, connecting an SSH client application with an SSH server. Common applications include remote command line login and remote command execution, but any network service can be secured with SSH. The protocol specification distinguishes between two major versions, referred to as SSH1 and SSH2. The most visible application of the protocol is for access to shell accounts on Unix-like operating systems, but it sees some limited use on Windows as well. In 2015, Microsoft announced that they would include native support for SSH in a future release. SSH was designed as a replacement for Telnet and for unsecured remote shell protocols such as the Berkeley R-Login, RSH, and Rexic protocols. Those protocols send information, notably passwords, in plain text, rendering them susceptible to interception and disclosure using packet analysis. The encryption used by SSH is intended to provide confidentiality and integrity of data over an unsecured network, such as the Internet. Although files leaked by Edward Snowden indicate that the National Security Agency can sometimes decrypt SSH, allowing them to read the content of SSH sessions. Definition: SSH uses public key cryptography to authenticate the remote computer and allow it to authenticate the user, if necessary. There are several ways to use SSH. One is to use automatically generated public-private key pairs to simply encrypt a network connection, and then use password authentication to log on. Another is to use a manually generated public-private key pair to perform the authentication, allowing users or programs to log in without having to specify a password. In this scenario, anyone can produce a matching pair of different keys. The public key is placed on all computers that must allow access to the owner of the matching private key. While authentication is based on the private key, the key itself is never transferred through the network during authentication. SSH only verifies whether the same person offering the public key also owns the matching private key. In all versions of SSH, it is important to verify unknown public keys, i.e., associate the public keys with identities, before accepting them as valid. Accepting an attacker's public key without validation will authorize an unauthorized attacker as a valid user. Key management. On Unix-like systems, the list of authorized public keys is typically stored in the home directory of the user that is allowed to log in remotely. In the file .SSH, authorized _keys. This file is respected by SSH only if it is not writable by anything apart from the owner and root. When the public key is present on a remote end and the matching private key is present on the local end, typing in the password is no longer required. Stack may need this password-less access to run properly. However, for additional security, the private key itself can be locked with a passphrase. The private key can also be looked for in standard places, and its full path can be specified as a command line setting. The SSH keygen utility produces the public and private keys, always in pairs. SSH also supports password-based authentication that is encrypted by automatically generated keys. In this case, the attacker could imitate the legitimate server side, ask for the password, and obtain it. However, this is possible only if the two sides have never authenticated before, as SSH remembers the key that the server side previously used. The SSH client raises a warning before accepting the key of a new, previously unknown server. Password authentication can be disabled. Usage. SSH is typically used to log into a remote machine and execute commands, but it also supports tunneling, forwarding TCP ports and X11 connections. It can transfer files using the associated SSH file transfer or secure copy protocols. SSH uses the client-server model. The standard TCP port 22 has been assigned for contacting SSH servers. An SSH client program is typically used for establishing connections to an SSH daemon and accepting remote connections. Both are commonly present on most modern operating systems, including Mac OS X, most distributions of GNU Linux, OpenBSD, FreeBSD, NetBSD, Solaris and OpenEVMs. Notably, Windows is one of the few modern desktop server OSs that does not include SSH by default. Proprietary, freeware and open-source versions of various levels of complexity and completeness exist. Native Linux file managers can use the FISH protocol to provide a split-pane GUI with drag and drop. The open-source Windows program WinSCP provides similar file management capability using PuTTY as a backend. Both WinSCP and PuTTY are available packaged to run directly off of a USB drive, without requiring installation on the client machine. Setting up an SSH server in Windows typically involves installation. SSH is important in cloud computing to solve connectivity problems, avoiding the security issues of exposing a cloud-based virtual machine directly on the Internet. An SSH tunnel can provide a secure path over the Internet, through a firewall to a virtual machine. History and development. Version 1.x in 1995, Tatu Lanin, a researcher at Helsinki University of Technology, Finland, designed the first version of the protocol prompted by a password-sniffing attack at his university network. The goal of SSH was to replace the earlier R-Login, Telnet and RSH protocols, which did not provide strong authentication or guarantee confidentiality. Lanin released his implementation as freeware in July 1995, and the tool quickly gained in popularity. Towards the end of 1995, the SSH user base had grown to 20,000 users in 50 countries. In December 1995, Lanin founded SSH Communications Security to market and develop SSH. The original version of the SSH software used various pieces of free software, such as GNU libgmp, but later versions released by SSH Communications Security evolved into increasingly proprietary software. It is estimated that, as of 2000 update, there were 2 million users of SSH. Version 1.99 in January 2006, well after version 2.1 was established. RFC 4253 specified that an SSH server which supports both 2.0 and prior versions of SSH should identify its proto-version as 1.99. This is not an actual version but a method to identify backward compatibility. OpenSHA OSSH in 1999. Developers wanting a free software version to be available went back to the older 1.2.12 release of the original SSH program, which was the last released under an open-source license. Bjorn Grunwald's OSSH was subsequently developed from this code base. Shortly thereafter, OpenBSD developers forked Grunwald's code and did extensive work on it, creating OpenSH, which shipped with the 2.6 release of OpenBSD. From this version, a portability branch was formed to port OpenSH to other operating systems. As of 2005 update, OpenSH was the single most popular SSH implementation, coming by default in a large number of operating systems. OSSH meanwhile has become obsolete. OpenSH continues to be maintained and now supports both 1.x and 2.0 versions. Version 2.x SECSH was the official Internet Engineering Task Force's name for the IETF working group responsible for version 2 of the SSH protocol. In 2006, a revised version of the protocol, SSH2, was adopted as a standard. This version is incompatible with SSH1. SSH2 features both security and feature improvements over SSH1. Better security, for example, comes through Diffie-Hellman key exchange and strong integrity checking via message authentication codes. New features of SSH2 include the ability to run any number of shell sessions over a single SSH connection. Due to SSH2's superiority and popularity over SSH1, some implementations such as LSH and Drop-Bear support only the SSH2 protocol. Uses SSH is a protocol that can be used for many applications across many platforms including most Unix variants, as well as Microsoft Windows. Some of the applications below may require features that are only available or compatible with specific SSH clients or servers. For example, using the SSH protocol to implement a VPN is possible, but presently only with the OpenSSH server and client implementation. For login to a shell on a remote host. For executing a single command on a remote host. For setting up automatic login to a remote server. Secure file transfer, in combination with rsync to backup, copy and mirror files efficiently and securely. For forwarding or tunneling a port. For using as a full-fledged encrypted VPN. Note that only OpenSSH server and client supports this feature. For forwarding X from a remote host. For browsing the web through an encrypted proxy connection with SSH clients that support the SOX protocol. For securely mounting a directory on a remote server as a file system on a local computer using SSHFS. For automated remote monitoring and management of servers through one or more of the mechanisms discussed above. For development on a mobile or embedded device that supports SSH. File transfer protocols. The secure shell protocols are used in several file transfer mechanisms. Secure copy, which evolved from RCP protocol over SSH. rsync, intended to be more efficient than SCP. SSH file transfer protocol, a secure alternative to FTP. Files transferred over shell protocol, released in 1998, which evolved from Unix shell commands over SSH. Architecture. The SSH2 protocol has an internal architecture with well-separated layers, namely, the transport layer. This layer handles initial key exchange as well as server authentication, and sets up encryption, compression and integrity verification. It exposes to the upper layer an interface for sending and receiving plain text packets with sizes of up to 32,768 bytes each. The transport layer also arranges for key re-exchange, usually after 1 GB of data has been transferred or after 1 hour has passed, whichever occurs first. The user authentication layer. This layer handles client authentication and provides a number of authentication methods. Authentication is client-driven. When one is prompted for a password, it may be the SSH client prompting, not the server. The server merely responds to the client's authentication requests. Widely used user authentication methods include the following. Password. A method for straightforward password authentication, including a facility allowing a password to be changed. Not all programs implement this method. Public key. A method for public key-based authentication, usually supporting at least DSA or RSA key pairs, with other implementations also supporting X509 certificates. Keyboard interactive. A versatile method where the server sends one or more prompts to enter information and the client displays them and sends back responses keyed in by the user. Used to provide one-time password authentication such as SSH or secured. Used by some OpenSSH configurations when PAM is the underlying host authentication provider to effectively provide password authentication, sometimes leading to inability to log in with a client that supports just the plain password authentication method. GSS API authentication methods, which provide an extensible scheme to perform SSH authentication using external mechanisms such as Kerberos 5 or NTLM, providing single sign-on capability to SSH sessions. These methods are usually implemented by commercial SSH implementations for use in organizations, though OpenSSH does have a working GSS API implementation. The connection layer. This layer defines the concept of channels, channel requests and global requests using which SSH services are provided. A single SSH connection can host multiple channels simultaneously, each transferring data in both directions. Channel requests are used to relay out-of-band channel-specific data, such as the changed size of a terminal window or the exit code of a server-side process. The SSH client requests a server-side port to be forwarded using a global request. Standard channel types include shell for terminal shells, SFTP and exec requests, direct TCP/IP for client-to-server forwarded connections, forwarded TCP/IP for server-to-client forwarded connections. The SSH FPDNS record provides the public host key fingerprints in order to aid in verifying the authenticity of the host. This open architecture provides considerable flexibility, allowing the use of SSH for a variety of purposes beyond a secure shell. The functionality of the transport layer alone is comparable to transport layer security. The user authentication layer is highly extensible with custom authentication methods, and the connection layer provides the ability to multiplex many secondary sessions into a single SSH connection, a feature comparable to BIP and not available in TLS. Enhancements. These are intended for performance enhancements of SSH products. SSH over SCTP. Support for SCTP rather than TCP as the connection-oriented transport layer protocol. ECDSA. Support for elliptic curve DSA rather than DSA or RSA for signing. ECDH. Support for elliptic curve Diffie-Hellman rather than plain Diffie-Hellman for encryption key exchange. UMAC. Support for UMAC rather than HMAC for MAC integrity. Vulnerabilities. SSH1. In 1998, a vulnerability was described in SSH 1.5 which allowed the unauthorized insertion of content into an encrypted SSH stream due to insufficient data integrity protection from -32 Costa Rican colons used in this version of the protocol. A fix known as SSH compensation attack detector was introduced into most implementations. Many of these updated implementations contained a new integer overflow vulnerability that allowed attackers to execute arbitrary code with the privileges of the SSH daemon, typically root. In January 2001, a vulnerability was discovered that allows attackers to modify the last block of an IDEA encrypted session. The same month, another vulnerability was discovered that allowed a malicious server to forward a client authentication to another server. Since SSH1 has inherent design flaws which make it vulnerable, it is now generally considered obsolete and should be avoided by explicitly disabling fallback to SSH1. Most modern servers and clients support SSH2. CBC plaintext recovery. In November 2008, a theoretical vulnerability was discovered for all versions of SSH which allowed recovery of up to 32 bits of plaintext from a block of ciphertext that was encrypted using what was then the standard default encryption mode, CBC. The most straightforward solution is to use center mode instead of CBC mode, since this renders SSH resistant to the attack. Undisclosed vulnerabilities. On December 28, 2014, Der Spiegel published classified information leaked by whistleblower Edward Snowden which suggests that the National Security Agency may be able to decrypt some SSH traffic. The technical details associated with such a process were not disclosed. Standards documentation. The following RFC publications by the IETF SECSH Working Group document SSH2 as a proposed Internet standard. RFC 4250, the Secure Shell Protocol assigned numbers. RFC 4251, the Secure Shell Protocol architecture. RFC 4252, the Secure Shell Authentication Protocol. RFC 4253, the Secure Shell Transport Layer Protocol. RFC 4254, the Secure Shell Connection Protocol. RFC 4255, using DNS to securely publish Secure Shell key fingerprints. RFC 4256, Generic Message Exchange Authentication for the Secure Shell Protocol. RFC 4335, the Secure Shell Session Channel Break Extension. RFC 4344, the Secure Shell Transport Layer Encryption Modes. RFC 4345, Improved ARC4 modes for the Secure Shell Transport Layer Protocol. It was later modified and expanded by the following publications. RFC 4419, Diffie-Hellman Group Exchange for the Secure Shell Transport Layer Protocol. RFC 4432, RSA Key Exchange for the Secure Shell Transport Layer Protocol. RFC 4462, Generic Security Service Application Program Interface Authentication and Key Exchange for the Secure Shell Protocol. RFC 4716, the Secure Shell Public Key File Format. RFC 4819, Secure Shell Public Key Subsystem. RFC 5647, AES Galois Countermode for the Secure Shell Transport Layer Protocol. RFC 5656, Elliptic Curve Algorithm Integration in the Secure Shell Transport Layer. RFC 6187, X 509 v3 Certificates for Secure Shell Authentication. RFC 6239, Suite B Cryptographic Suites for Secure Shell. RFC 6594, Use of the SHA-256 algorithm with RSA, Digital Signature Algorithm, and Elliptic Curve DSA in SSHFP resource records. RFC 6668, SHA-2 Data Integrity Verification for the Secure Shell Transport Layer Protocol. RFC 7479, ED 25519 SSHFP resource records. In addition, the OpenSH project includes several vendor protocol specifications, extensions, OpenSH Protocol Overview, OpenSH Certificate, Key Overview,